Hello everyone, welcome to another robotics session. So far we talked about rigid body motion and how you can use that to develop homogeneous transformation matrices. Using those matrices we build forward kinematic equations. We show that using DH convention you can do it systematically. And the forward kinematics equation would give us the robot end effector position and orientation as a function of the joint variables. Now, this is the way we look at the robot is in a static environment. Now, what if we want to think of the velocities? How would the velocity of the robot environment, robot end effector change if we change the velocity of the robot joints? This is an interesting way to look at the robots, and we will show that actually by analyzing the velocity of the robot end effector, we can get quite a lot of information about how a robot behaves. First thing, how can we calculate robot's end effector velocity? The forward kinematic equations is given as something like this, where actually the robot end effector can have several parameters. If you're interested in position, its position is given by x, y, z. If we're interested in orientation as well, we can get them using three Euler angles. And the forward kinematics gives us as a function of joint variables. And the joint variables we assumed has dimension n. This would be our joints. And depending on how we look at the robot end effector, we might have from 1 to m different dimensions. So this would be our end effector. For instance, if we're just interested in the position, x, y, z position, the dimension of the workspace where the end effector is only 3, m is 3. If we have 3 joints, dimensions of q joints are also 3. This is the forward kinematics. How can we use that to get robot end effector velocities? Let's take the derivative of this equation. Using the chain rule of differentiation, we can expand the term on the left, the term on the right as basically partial differential of forward kinematic with respect to the joint variables times joint variables with respect to time. And simply it is basically velocity of the robot end effector is a function of derivative of forward kinematics with respect to joint variables times velocity of the joint's inputs. This is a nice equation that gives us velocity of end effectors as a function of velocity of joints. But what is this matrix? This is something that we call Jacobian. Let's calculate Jacobian. So we're interested in finding this matrix. Forward kinematics K is a vector function. Q is also a vector. We have several joints. What is the derivative of a vector with respect to vector? If you remember from calculus, this is a gradient function. Consider K is K1 to Km, which itself is a function of n q's. Let's repeat the process of finding velocity only for one element. Let's say the x element of the robot end effector position. X dot would be K1 dot. Using chain rule of differentiation, it is equal to this term. If we repeat this for other elements of the forward kinematics, we can get similar equations. Now, if we put this in a matrix format, it would look like this. Basically, end effector position and orientation is that matrix times q dot, and we can see what that matrix X based on comparing these two equations. That matrix actually would look like this. This is a gradient. This is a derivative of vector with respect to a vector. And in the forward kinematics, when we take this derivative and calculate this, we call this matrix Jacobian. This is all we need to estimate velocity of robot end effector. With this equation, so considering this case that end effector has two variables, size of m is 2 here, and we have 3 joint inputs. Simply by taking derivative with respect to time, we can calculate the Jacobian that would give us velocity of robot end effector as a function of velocity of the joints, and this term we showed is called Jacobian, partial derivative of forward kinematics with respect to joint variables. When calculating this, it's always good to look at the dimension of vectors so you know you're getting it right. Dimension of our end effector velocity is m by 1, in our case 2 by 1 here. Joint inputs were 3, were n by 1, or in this case 3 by 1. Then size of the Jacobian should be m by n, in this case 2 by 3. So this can be cancelled out and would give you the 2 by 1 end effector. And once we have the Jacobian, the velocity simply can be calculated using this equation. Let's calculate it for a simple SCARA robot. Remember previous video, we found the forward kinematics of a SCARA robot as this. Now, what is its Jacobian and velocity kinematics? Taking the derivative of this with respect to time and use the Jacobian equation, we can calculate it as actually our end effector velocity position and let's say or angle velocity is Jacobian times our joint variables where there were 3, theta 1 dot, theta 2 dot, d 3 dot velocity of the joint. And what is Jacobian? Using the equation that we derive. Derivative of this one with respect to the first joint input, theta 1. Derivative of the same with respect to second input, theta 2. Derivative of it with respect to third, d3, there's nothing, 0. Repeat this for the others. Sorry, this was sinus. And the last one, d3, with respect to theta 1, 0, 0, and with respect to itself is 1. Finally, for the last one, derivative with respect to theta 1 is 1, 1, 0. This is our Jacobian, and plug it in this equation, we can calculate the forward velocity kinematics. Now, estimating Jacobian is very straightforward, and if we want to have a recap, so far we found a way to get the robot's forward kinematics. We can get the velocities as well after we calculated forward kinematics. All we need to do is get the Jacobian from forward kinematics, and then this would give us the velocity of robot end effector as a function of joint velocities. Now, Jacobian is a very interesting matrix, and it gives us a lot of information about a robot. But just by looking at its dimension, we show that its dimension is actually m by n. When you see a Jacobian, you can instantly tell that this robot has n joints and m dimensionality in its n effector. So just by looking at Jacobian, you can get the information about degrees of freedom of the robot. Jacobian gives us a lot of useful information, and in the next videos we're gonna talk about some of the features of Jacobian.